So we are going to continue. So today we are going to have some discussion about isometries and related things. Isometries in the context of linear transformation or finite dimensional vector spaces. But basically, what we are going to see is isometries in terms of unitary transformation. So we first define a typical case of a unitary transformation, which is characterized by, for example, from an heuristic understanding, the sufficient condition for a linear transformation, particularly in the complex, if we take a complex space into consideration, is that it's like this. But the other way of saying this is that if this U dagger is U inverse, so this is a typical case of an orthogonal and unitary transformation where the product space may be real or complex. That's the thing. So that U star is one, or you might have, if you see the course in matrix algebra, U dagger is one. Yeah, that's the thing. So here we are going to see this condition where either U star is one or U star U is one in both conditions. So we are doing the same thing within the context of the linear transformations and how we have unitary transformations to that context. So there are three conditions to that effect. Three conditions. On a linear transformation, u on an inner product space. So we are interested in the product space is the inner product space, in which if you have if you the space that dual space is symmetric Hermitian, if you remember the way we have constructed it that way. So if the conditions for a linear transform for U on an inner product space on or equivalent. So for a linear transformation which on an inner product space which are equivalent to each other, the conditions which ought to be satisfied are U star U is 1, the other is this is 1, the second is Ux Uy is x of y for all x and y. The third is modulus of Ux is modulus of x for all x. So these are the three conditions. So we are going to use our previous logic. This follows this, and this follows this, and you come back to this. This is the one way of trying to say the self-consistency of these statements in a framework. So if the proof of it is very simple. For example, proof is that if one holds, then U of x, U of y is a part of. So you can, if U is equal to U dagger, so if U is U dagger, you can say it. You can also use U dagger, or because U dagger is 1, so it doesn't matter x y, or again, so it's equal to x of y. So the first, so from this we have arrived at this, so in a simple. And for x and y in particular. For example, so if u dagger is 1, so u dagger its modulus of that will be 1, sort of thing. So this means u of x modulus will be equal to x square. Sorry, modulus. Uh, so the so or from this you can say ux is equal to x, or ux is equal to x. Sorry. So you can, so from this you have to, from this, and the third should imply that it's u, just if x is y, then this means u of x minus u of y modulus is x minus y. So from this you follow this. So you can see in a simple way construction. So now the important point is that so these properties should, for example, the way we have isomorphisms, and sometimes we have linearity preserving properties, which you say they are isomorphic. So you have a space and you have a dual space. So an element in this space is dual to another space. So there is a connection. So there is some, if you just have a geometrical way of trying to visualizing these vector spaces, so you can say, so they are distance preserving constructions as such. Um, so in that sense, so if you say these inner product spaces, they are complex inner product spaces and they are following these properties, they also have these inner distance preserving linear transformations. That's the precise way of saying that. And we can say that there is an isometry. Such transformations, these are used by the word called isometry. Isometry is a very general word, but in the context of finite dimensional spaces, which are necessarily orthogonal finite dimensional vector spaces, which are orthogonal or unitary, because the word unitary contains both real as well as complex vector spaces, whose inner product is somehow gives a certain value in those dual spaces. Uh, and on a finite dimensional spaces, further this U inverse is equal to U, this is the property. So in algebraic systems, they are sometimes called automorphic systems. Means you operate. We also previously studied symmetry functions. We have a function, we have a symmetry function. You get to the function back. In the same context, you have automorphic functions where there is a one-to-one mapping, one-to-one mapping, one-to-one mapping onto itself, which are going to preserve all the structural relationships among its elements. The structural relationship among, so in the same way, it's isomorphic, preserving this thing. So in the same sense, we have isomorphism or inner product species which are distance preserving structures in that context, which includes lengths and distances. And if you have two dimensions, this becomes more pronounced. This thing is that one important thing is, can we generalize that one triviality, not triviality, we can say one point is that whether we can see this distance preserving property to infinite dimensional vector spaces as a side comment. But if we think of finite dimensional spaces as part of some infinite dimensional vector spaces, So, and whether those finite dimensional vector spaces are complete in itself or not. That's it. Huh. So there is no common. So in infinite dimension, we have not. This course is mostly about finite dimensional vector spaces, but in infinite dimensional vector spaces, though there is no common analog of, for example, how to preserve these orthogonal and unitary transformations in the simultaneous manner. Yes, yes. So these automorphisms are basically the distance preserving, length preserving algebra for finite dimensional spaces is mostly described. Now the point is, can we? So we have normally talked of orthogonal transformations, but the proper way is, can we change proper formulation is, can we change of orthonormal basis. Orthonormal basis. So orthogonal is a particular way, but so we have in the previous thing tried to see how we study orthonormal basis and its for the similarity with the properties of conical delta functions in terms of that matrices. So, but the point is whether we can change one orthonormal basis to the another, and what's the relationship between the two. If one of them is inner producting, the inner product preserving the algebra. So how we can make this map to its dual space, which may be orthonormal. So if I just use the thing that if so how we can pass from one inner product basis to orthonormal basis to another basis. So that's our job. Yes. So to do that, we are going to first have a theorem stated. So I'll just state a theorem. Theorem states that if Chi is a vector space having elements, it is an orthonormal basis. Is an orthonormal basis of an n-dimensional vector space of an n-dimensional inner product space and if you use an isometry on V, then Ux is Ux1 so on and Uxn is also an orthonormal basis of V. So if X is this, it is also of an inner product space, and if U is a, so here we finite dimensional is it's an n-dimensional finite dimensional inner product space V, and U is an isometry on V, then so it should also have an if it's an if it has an orthonormal basis U, it should also have this orthonormal base in this space. Conversely, if U is a linear transformation and Chi is an orthonormal basis, with the property that U is also an orthonormal then U is an isometer, then U is an isometer. So that's the point. So if this is an and then product space, and U is an isometry in V, so the point is that so it's also this thing. So conversely, if U is a linear transformation chi orthonormal basis, so you have to say so if there is a space and there is a dual space. So if there is an orthonormal n-dimensional finite vector space, so it has inner product space. If it's an isometry in, so it's going to also have isometry in the original space as well as dual space. And the other is if it is a linearity preserving transformation, so then back based in orthonormal. This property is also an orthonormal basis. Then U is isometric. That's fine. So it's an isometric. So it means distance preserving or length preserving algebra is contained in it. So in the first case, if so, it's again if there's an isometry between two the things, they are between so if there is an isometry between two finite dimensional vector spaces, this means that if one of them has orthonormal basis, other will also have orthonormal basis. And conversely, if 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 there are two finite dimensional vector spaces, both of them are orthonormal, this means they should preserve isometry. So these are this the statement of this theorem. And the proof is again very not that complicated. So the proof is you have uxi, can be defined as, and U is defined as isometry. U is xi, these are the elements xi, xt. So here you have that how we define orthonormal basis. If I is equal to j and I is not equal to j. If for I not equal to j, it's 0. For I is equal to j, it has some value. So follows that U, from this you follow that U chi is an orthonormal set along with chi. So if it's complete, it is complete if chi is this x is 0 for I n. So for same I is equal to j, I not equal to j. For ij, different things it's 0. For this it means u star x xi is 0 or u star x or u is 0. So conversely, if ux is an orthonormal set along chi, we have ux, we have ux, uy is xy for all x and y. So if we have a sort of a matrix, a way of also looking at these things, if it represents a matrix where u, I, j, I and j are the rows and columns represented by the isometric transformation. So then it should satisfy this condition. It should satisfy this condition. UKI, UKJ. So it should be delta IJ. So this, so if you see K can be repeated, you can just conjugate it, so it will be back. You can write it like this. You can write it like this. You can write it like this, that UKI UKJ conjugate is delta IG, and this means U dagger. So it's a sort of, you can also see it. It's this U is one. So it's also this is satisfying a sort of this is known as isometric matrix. Isometric matrix. So if we have defined these orthonormal bases, and they are having these properties, so we can construct them in terms of some matrices, product of two matrices, which are defined two vector spaces and two orthonormal bases. So you can, which this preserves this, it's going to preserve this algebra, or it's going to preserve this UDAG, which was previously defined for how among the properties of isometries in that sense. So there is also another way of saying how we can make a triangular matrices, upper triangular or lower triangular matrices using this property. And even though the way we can from Gram-Schmidt or orthogonalization condition, how we can construct a given matrices which is not complete. We can use that. Now, in the same way, there's another thing called perpendicular projections. So what are, so if you what are the, if you want to have, how we can projection. So it's how we can investigate a particular decomposition of, for example, V is a vector space in terms of this. The other is called, so M perpendicular is uniquely determined by a subspace, determined by subspace So we have a space, subspace, and this is uniquely determined under subspace. Now the theorem says a linear transformation E is perpendicular projection if and only if and only if and only if E square is equal to E conjugate. No, sorry, E star. So there's a particular property of idempotent property where the matrix, the square of matrix gives the matrix back. So there are typical cases of matrix properties, matrix algebra, which are defined by idempotent matrix, which the square of that matrix gives the matrix back. Now the point here is how we can define a finite dimensional vector space which has a linear transformation, and we have a projection space which is also a subspace. So how we can decompose that product? It is as if the properties is similar to that of idempotent matrix. So perpendicular projections or positive linear transformations. The way we have semi-definite properties, in the same way they have a property such that Ex is less than or equivalent to x mod of x for all of x, or mod of x is greater than this. So now we have to just have some steps. We are going to show this thing. So by theorem 45, so if you go to there for perpendicular projection, we have this idempotent property. So it's previously defined. So proved in section 45. So we will not go there. So E is equal to E square is equal to E star. So now what we are going to say, we have to only show that R and this are orthogonal, these two. So if they are preserving this property, so we can show that they are, you have to show these vector spaces are orthogonal. And for this purpose, so let X be, so this is, if we take R, E is one other vector space, and this is another vector space which is perpendicular, and they are arranged in the null space, the perpendicular projection, they are the null space. So we only have to show that they are orthogonal. We have to only show that they are orthogonal. And for that purposes, so let X be any element of R and Y be any element of this projection, this projection. This is element of this, and this is element of this projection space. So the desired result is, so we can also write, so the X, Y element of one, and this is the element in another. We can write it in terms of projection space. So Ex, Y can also be written as, if you just change the order of them, it should not by linear, so E will go from this, but it will be conjugate from this side. Or X times EY should be 0. Because of that, it's orthogonal in that sense. So the positive character satisfying E is E square is equal to E this, or from this you can say Ex, you can see it, you can define it. So if you multiply E is E square, if you multiply it by E square, it will be E and Ex. So it will be E square X into X. Now if you want to change this from linearity, so it will be X E conjugate star X. Yes. And again, if you want to get E back, you can have EX. Yes. Again, if you want to take mod of it, it will be modulus of EX square. Yes. It's greater than 0. Now, why it's greater than 0? That's the point. Now we are going to change it. So if X is Y, so it will be X square. So X square minus this thing, modulus of, so we are going to come from this step and this step. And if X is equal to, so it will be subtracting the two, X square minus E square will be equal equivalent to x of x minus, so you can write it otherwise also. You can write it as minus e times x of x. So if it's x is equal to x, so it will be e square. So what we are going to do, so subtract this and this. So you can say it is equal to as a, so we have gone from this to now bracket. Probably we will define a bracket for this. So it will be 1 minus e times x into x. 1 minus e, 1 minus e, 1 minus e times x into x, sorry, 1 minus e times x into x. This is greater than or equal. So this concludes the proof of the theorem. So it was a thing that if we define this statement was that how we define a projection which is perpendicular to a given subspace, a space and a subspace, and that subspace is a perpendicular subspace. So how we can define a linear transformation which has this idempotent property, satisfying this. So from this we can show the proof is there. So what important thing is that so the important which I will not prove, but the statement is very important. The statement says that so it comes from an understanding of these perpendicular projections that sums and differences of adjoint transformations or self-adjoint. That's fine. So they are adjoint, but product of two self-adjoint transformations is self-adjoint only if they commute. Means A and A plus B. This so if there are two transformations, sums and differences, A plus as well as A minus. So you can say it A minus. So you can say B has A and minus. So it's self-adjoint, they are self-adjoint. But the product will be only, in case of product transformation, it will be only if they have a commuting property. So this commuting property can be exploited later. The way we had the linearity preserving property actually was not satisfied in that sense. So we had to start at the start of the course try to see that linearity preserving property maybe it's not only products of two things, they will not always commute. They can also commute if the individual elements commute. I don't remember exactly. So the point is that this property it follows from that. So for the understanding of it, you have to go yourself for the next section, which I skipped for this thing. And we can also have how we can combine the perpendicular projections. That's the thing. Oh, that's one. So these can be, once we combine these projective transformations, which again we have one space and the other is the subspace. How we can combine these these transformations? They may be algebraic or geometric objects in two considerations which we have. We can have algebraic or geometrical intuition can be attached to them if you want to understand things in those contexts. So now the last today is how complexify, complexification. So this is an important thing. So previously also we saw that how we once we are introducing this integral product species, we were very it was that once we make transformation from real to complex species for the inner product. To be positively definite or to be preserving something, it should be symmetric conjugate. That's it. And there can be some properties where the operations defined in these real vector spaces may differ from complex vector spaces. So there is always, it's be interesting exercise how we can go from how we can complexify a real vector space into a complex vector space or vice versa. Or we can have a complex vector space and how we can extract real space out of it, subspace out of it, and what can be interesting divergences or whatever these things are. So here what we are going to do is now we are going to we're going to so there are theorems that are true for both real and complex spaces. And there are theorems which are true here in complex spaces, but they may not be not true for real spaces. So that's how we have interesting details. So the point we are going to see is how we can first complexify a real vector space in the simplest case. So if we have a if V is a real vector space, and V plus is a set of all ordered pairs with both x and y in V. So we define sum of two elements V plus as x1 y1 for one space to x2 y2 is a network for another case. So the sum can be so x1 plus x2 and y1 plus y2. But the point is, if we define the product of elements V plus by complex number, so we will introduce alpha plus iota B. Then what can you say? So alpha plus iota B into xy will be equal to, so you can see it, alpha x beta y, so it will be alpha x minus beta y beta x plus alpha y. So here maybe this x xy is x plus iota y. So that's why x and iota y. So you can have alpha x iota square. So that's why minus beta y. Beta y x and alpha y. So if you just study the straightforward and slightly laborious computation shows that set V plus becomes complex vector space with respect to these definitions of linear operations. So we should straightforward computation. So it's an exercise. Just do it. So that this is a complex vector space. If we have linearity. Now, if we want to extend, you can read the section of it. If we want to extend it for bilinear functionals, if you remember, there are certain the properties of brackets when we define bilinear functionals in terms of that bracket formalism. So, in the same context, how we can extend bilinear functionals for conjugate bilinear functions. For example, if V is a real inner product space, so there is a natural way of introducing a complex inner products. We are going to introduce a complex inner product into V plus, and we write a definition x1 plus iota y1 x2 plus iota y2 can be written as x1 x2 y1 y2 x iota y2. So we can x iota y2 iota we can get outside. So we can write it like x1 y2. In the same way y1 x2 y1 x2. This y1 x2. And we can observe if x and y are orthogonal, then x plus iota in V, then x plus iota y square is mods of x square is mods of y square. So the correspondence from A to A plus, which are there, so they should satisfy all the algebraic properties or transformations they should satisfy. Now, if you remember, we had used one is matrices, the other is skew matrices. We defined C in terms of A plus B and C in terms of A minus B, where A and B are complex matrices previously also. So like that B is alpha A, alpha is the scalar, and B dagger is, this is called alpha A plus C, sorry, alpha A plus C is A plus B, C plus is A plus B plus, and B is having properties of this, and B plus is properties of A plus. And if we evaluate as these as linear transformations, where A plus has, for example, proper vector x plus iota y, so alpha plus iota beta, and x and y are in V, and alpha and beta are real, then we can have Ax can be written as alpha x minus beta y, Ay can be beta x plus alpha y. So then the subspace V spanned by x and y is invariant under E. Is invariant under E. So maybe for dimensions 1 and 2 can show it in a very simple way. So you can say that the matrix of linear transformation A on V with respect to some basis x in V is the same as the matrix A plus on B plus with the basis of x in B plus. So these are two linear transformations. So this root of the so this is the comment of this how can do complex equations. So you can say that matrix transformations in real spaces can be shown as if there are matrix transformations in the complex spaces. So this is how we try to characterize them in this simple sense. So we're going to stop here to discuss.